The objective of this lab is to demonstrate surface mapping using the electronic level or autocollinator. Establishing a reference plane is often prerequisite to measurement or fabrication procedures. Relative to this reference plane, points can be established either within the plane or outside of the plane. Measurement of a surface's deviation from plane is typically performed with an electronic level or an autocollinator. Whether measuring the axis of motion of a translating carriage or the area of a surface plate, the technique is fundamentally the same. Uniformly spaced points are located along a measurement path. Angles between adjacent points are measured. These angles are converted to height differences, and a profile of the measurement path is plotted from the relative heights of the sampled points. In our measurement, we wish to record the general shape of the surface or the very low frequency waviness present in the surface. Consider the height measurement of this specimen using a surface plate and an indicator. The base of the indicator stand and the bottom of the specimen will provide some averaging or filtering of the high frequency surface waviness. Therefore, we should concern ourselves with measuring the very low frequency waviness, which will influence the repeatability of the height measurements over the area of the surface plate. To map a line profile, an angular measurement device is used to obtain the tilt of the measurement path segments defined by the spacing of the device's feet. In practice, a straight edge is normally used to ensure that the measurement path is followed. The measurement device is carefully positioned at the initial position. Two techniques can be used when initiating a series of measurements. The tilt reading at the first measurement position, that is, the tilt between points P1 and P2, can be zeroed, or the initial measured tilt can be recorded. A non-zero initial tilt value will not affect the final measured profile. The measurement device is now carefully positioned at the second position. That is, the rear foot of the device is now precisely placed where the front foot was located in the first position. The tilt reading for this second segment is recorded. In this manner, the measurement device is stepped through each of the measurement positions and tilt values are recorded for each of the past segments. When values have been recorded for all of the segments, the tilts are now converted to displacements. Since we have a known foot spacing and a measured angle, we can calculate the corresponding vertical deviation of the surface. With the height variations greatly magnified, the points along the path can now be plotted. The first point, P1, is arbitrarily set to 0. The second point is placed relative to the first. The third point is placed relative to the second, and so on. To make the results more intelligible, the slope is removed by holding the first point at 0 and adjusting the last point to 0. We can now see that this path across the surface has a peak-to-valley deviation of 83 microinches. The Union Jack method is often used to correlate data from individual measurement paths into an overall map of the surface area. This technique gets its name from the British flag pattern which the connected paths form. Compass points are often used to help identify particular measurement paths. In this nomenclature, the diagonals would be the northwest to southeast path and the northeast to southwest path. Observe that the measurements along the diagonal and vertical paths are made from north to south, and that the measurements along the horizontal paths are made from east to west. Note also that the proportions of the short side, long side, and diagonal are 3, 4, and 5. Furthermore, to ensure profile intersections always occur at data points, the minimum number of sampling segments on the short side is 6. Before the profiles are joined, each profile is adjusted so that its endpoints are 0. The key to this method is the order in which the data from the individual paths is assembled. The first two profiles to be connected are the diagonals. To join these two profiles, the diagonal with less deviation must be adjusted to fit the center point of the diagonal with the greater deviation. Next, each side profile is adjusted so that its endpoints fit the corner points established by the diagonals. Each of the centerline profiles is now adjusted so that its endpoints fit the midpoints of the sides which it joins. Note that 3 values have been generated for the central data point, one established by the diagonal with the greater deviation, one specified by the vertical center line, and one provided by the horizontal center line. The validity of the data can now be verified by checking the agreement of these 3 central data points. Valid data is typically associated with agreement of these 3 values to within 50 microinches. That is, the highest and lowest values do not disagree, by more than 50 microinches. If this condition is not met, a complete set of new data should be collected. Once the validity of the data has been established, the data points can be plotted on a plan view of the surface or can be used to construct a three-dimensional map. As I stated earlier, two instruments are commonly used for measuring surface profiles, the electronic level and the autocollinator. In the case of the electronic level, a pendulum and a shaded pole inductor circuit are used to sense the tilt resulting from the height difference of the two sampled points. The measured angle can be read from the analog meter on the console or can be represented by the console's plus or minus 10 volt analog output signal. A choice of measurement ranges is available, with the largest range being plus or minus 1,000 arc seconds. The best resolution found on the smallest measurement range is a half an arc second. Note that this unit allows differential level operation. The level's shaded pole inductor circuit consists of a laminated core with one central primary coil and two secondary coils. A 5 kilohertz AC voltage generates a current in the primary winding. This current induces a flux in the central core. When the system is free of external influences, the flux in the central core is equally distributed in the two halves of the core ring. When the two flux components are equal, the induced currents in the two secondary coils are equal and opposite, thereby causing the measurement output voltage to be zero. When a shading loop, that is a thin conducting loop, typically copper, is placed around the middle of the core ring, current is induced in the loop by the two flux components. If the loop is precisely located at the center, each flux component contributes equally to the induction of the current in the loop. With the flux components still equal, the output voltage remains zero. However, if the loop is moved away from the center, the side to which the loop was moved will contribute more towards inducing the loop current and will therefore have a smaller flux component. The smaller flux component will now result in a smaller induced current in that side's secondary coil. Since the currents are no longer equal and opposite, a non-zero output voltage will now be measured. This output voltage is linearly proportional to the loop's displacement from the center position. The pendulum is suspended from the level's housing by two flexures. Attached to the pendulum is the shading loop. As the level is tilted, the shading loop is displaced from the center as the pendulum seeks to maintain its vertical orientation. Given the pendulum length, the spacing of the level's feet, and the proportionality constant which relates the loop displacement to the output voltage, we can read the output voltage from the console's analog display and calculate the height difference between points P1 and P2. Ideally, the surface being mapped should remain in its original orientation without any changes in tilt during the measurement procedure. However, some applications do not allow this condition to be met. In those cases, a differential level system can be used. Such a system consists of two levels and a single console. Both levels are placed on the measurement surface. Level A remains stationary, while level B is moved along the measurement path. The console displays the difference between the tilt of the two levels. With two levels, the effect of the tilting surface will be canceled, and the output voltage will represent only the measurement path tilt from level B. While differential level operation does compensate for changes in the general tilt of the surface being measured, it does nothing to compensate for deflections of the surface during the measurement procedure. Therefore, it is most important to remember that the surface being measured must be rigid. Since the operation of the level involves a pendulum which tries to remain vertical despite the orientation of the housing, the general tilt in the surface can sometimes exceed the level's limits of measurement. In those situations, a shim can be placed under the level's lower foot to bring the reading into the range of the system. If the same shim is used throughout the measurement series along a path, then the thickness of the shim falls out of the calculations. However, extreme care must be taken to ensure that the shim is placed in the same position each time. As implied by its name, an autocollimator uses a beam of collimated light, that is, a beam of parallel rays of light, to measure very small angle changes. Operation of the autocollimator can be generalized as follows. A set of crosshairs is positioned in the path of the exiting collimated beam of light. Therefore, in a manner of speaking, the beam contains the image of the crosshairs in the form of a shadow. If a perfectly plane reflecting surface is placed orthogonal to the axis of the light beam, the beam will be returned back into the autocollimator, and the shadow image of the crosshairs will fall onto the crosshairs of the eyepiece graticule. A slight deviation from orthogonal orientation results in non-coincidence of the graticle crosshairs and the returning image. With a knowledge of the collimating lens focal length f and the distance d separating the graticle crosshairs and the image, the angle of deviation theta can be determined. Originally, the reflector's angular deviation from the orthogonal orientation was determined by the amount of rotation of the refractor element required to bring the target's crosshairs image into alignment with the graticle crosshairs. The refractor element would be manually or sometimes automatically rotated until the graticle crosshairs and the reflected image were aligned, and the angle would be read from the calibrated rotation mechanism. Advances in electronics have now relegated the eyepiece to use in instrument setup. Today's autocollimators use emitters and detectors to automatically sense changes in the reflector's angular orientation. The unit senses changes in the image position on a photodetector array, then automatically calculates and displays the changes in angle. Like all instruments, the autocollimator is not without problems. A major disadvantage of the autocollimator is its sensitivity to fluctuation in the beam's air path. This sensitivity to changes in the air path conditions can lead to measurement error. Furthermore, errors in the reflector surfaces can also contribute to measurement error. This autocollimator system, the Rank-Taylor-Hobson DA200, uses an infrared light source. The system has 1/10 arc second resolution and a measurement range of plus or minus 200 arc seconds for a working distance of up to 5 meters or 15 feet. System accuracy is dependent on both the measurement range and working distance used. Both attitude and altitude measurements can be made with this unit. The x-axis is the attitude axis with positive angles resulting when the left side of the reflector is closer to the autocollimator than the right side of the reflector. The y-axis is the altitude axis with positive angles resulting when the top of the reflector is closer to the autocollimator than the bottom of the reflector. To use the autocollimator, first connect the optical unit's cable to the appropriate connector on the rear of the electronic console. Place the optical unit on the 3-foot pads as shown. Note the use of kinematic mounting as the optical unit has 3 spherical feet. Kinematic mounting avoids overconstraint and the resultant lack of repeatability. Connect the console's power cable to a power outlet, making certain that the supplied voltage agrees with the voltage selected on the rear of the console. Turn the console on by pressing the mains push button. Allow time for electronic stabilization. Use a straight edge to ensure that the reflector is moved in a straight line along the measurement path. Again, note the use of kinematic mounting. The sled has 3 feet. Set the feet on the reflector sled to the desired spacing. Remember the trade-off nature of this parameter. Wide spacing of the feet can result in shorter wavelength variations being overlooked, while narrow spacing of the feet increases the number of measurement intervals and thus increases the chance of measurement error. In this exercise, the spacing of the feet is set to 2 inches to accommodate using the Union Jack pattern on an 18-inch square granite surface plate. Carefully position the reflector at the closest measurement position, making sure that the feet are positioned against the straight edge. Align the optical unit with the measurement path. Adjust the position of the optical unit until the image of the crosshairs comes into view. Continue to adjust the position of the optical unit until the graticle crosshairs and the returning image are aligned. Using the signal level knob on the front of the console, tune the signal level to the maximum level possible without causing the received signal meter to enter the red zone. The displacement indicator